In mathematics, a true function operates as a deterministic engine. You feed it a specific parameter, and it generates a single predictable outcome. The foundational rule of any function is consistency. One independent input must yield exactly one dependent output. Not all equations pass this test. Take the formula y squared equals x. Inputting a 4 produces two results, a positive 2 and a negative 2. Because one input generated multiple outputs, this equation fails the function rule. Contrast that failure with the linear function, y equals 3x plus 2. If you input a 3, the system calculates the math and outputs in 11 every single time. This reliability allows functions to act as translation engines. They convert abstract algebraic parameters into geometry, locking the input and output together as a single coordinate on a grid. Today, we are going to deconstruct the architecture of two foundational mathematical models, the constant linear function and the dynamic quadratic function. Translating these equations into geometric space bridges the gap between abstract algebra and physical reality. It provides the exact mechanism used to predict how complex systems will behave. On a Cartesian plane, the linear equation y equals ax plus b is defined by two specific constraints. The first constraint is the y-intercept, b, the baseline anchor when input x is 0. The second constraint is the slope, a. This dictates trajectory, calculating vertical change over horizontal change. These mechanical constraints can model how consumer demand responds to pricing. This graph plots demand for a retail product. At a price of $49, demand sits at 26,000 units. When the price increases to $51, demand drops to 16,000 units. Calculating the difference between these two coordinates yields a slope of negative 5,000. That negative slope defines the boundary of the market. For every dollar the price increases, demand decreases by exactly 5,000 units. If the slope drops to 0, the line flattens completely. A 0 slope dictates no vertical change. Regardless of how far the input moves horizontally, the output remains identical. If we rotate the line to be perfectly vertical, the mathematical model breaks. A vertical line implies an infinite slope. Because there is no horizontal progression, the trajectory requires dividing the vertical change by 0. Linear models execute perfectly for constant rates of change, but physical forces and markets often accelerate. To map that movement, the model must evolve. Because physical reality rarely operates at a locked, static speed, our mathematical architecture requires a structural upgrade. As the linear formula morphs into the quadratic equation, y equals ax squared plus bx plus c, the straight line on the grid bends into a curve known as a parabola. Squaring the variable curves the line. The rate of change is now tied to x itself. On a linear graph, tangent markers remain parallel. But on a parabola, tangent markers continuously shift their angles as they track along the curve. Concavity is governed by the leading coefficient, a. When a is positive, the parabola opens upward, modeling accelerating growth. When a is negative, the trajectory flips, opening downward. This curved geometry creates an absolute turning point, called the vertex. Locating this vertex is the primary objective in complex modeling. It represents the precise coordinate where a business achieves absolute maximum profit or minimum cost. Before reaching a peak, we must calculate exactly where the curve crosses the baseline, the points where the y value equals 0. The quadratic formula is the designated tool for identifying these x-intercepts. Within this calculation, the geometric reality of the system is dictated by a cluster of terms hidden under the square root. This expression is the discriminant. It serves as the threshold for what can physically occur within the model. In case 1, the discriminant yields a positive number. A positive value allows the square root to evaluate normally, triggering the plus or minus operation in the formula. This mathematical split produces two intersection points. On the graph, the parabola physically crosses the x-axis in two separate locations. Because these two coordinates stem from an identical plus or minus operation, they are always perfectly symmetrical to the vertex. In case 2, the discriminant equals exactly 0. The square root of 0 is 0. Adding or subtracting 0 neutralizes the plus or minus operation. Without that split, the system collapses to a single point of contact. The parabola shifts until it perfectly grazes the axis. Geometrically, the curve never intersects the baseline. The vertex itself becomes the sole x-intercept. Finally, we reach case 3. The discriminant evaluates to a negative number. The formula is now attempting to calculate the square root of a negative. Because squaring a real number produces a positive result, this operation is undefined. The equation yields 0 real solutions. On our geometric plane, the parabola hovers entirely above or below the baseline. The system modeled here never physically crosses the axis. The discriminant establishes the boundary condition that determines if an event will physically occur within a modeled system. Every algebraic parameter within these functions dictates a specific geometric blueprint. By locking down constraints like constant slopes and locating the exact coordinates of a vertex, we create predictable models of reality. Shifting the position of a variable creates a structural change in the growth rate. We can see this shift by comparing the quadratic structure against an exponential one. In the quadratic model, x acts as the base. Move x to the exponent position, and the resulting curve quickly outpaces the growth of the parabola. This positional shift allows the function to map compounding growth that outpaces squared models. As mathematical syntax evolves, our ability to decode and predict increasingly complex realities scales right alongside it. Mastering these foundational functions provides us with the ultimate toolkit to decode the invisible architecture governing the physical world.